Hello, this is my equations of uniformly accelerated motion presentation. I'm Akhil, grade 11, Wells International School. So what is this presentation about? The most important note to remember that is that this presentation is only for motion with uniform acceleration, and these equations that I'm going to be presenting and explaining can only be used for uniform acceleration. So before we move on to that, we need to clarify what is acceleration. Though in standard usage we have the idea that acceleration is the speeding up of an object, this is not necessarily the case in physics. In physics, acceleration is a vector quantity and it is dependent upon velocity. And velocity is a vector quantity that keeps into consideration the direction of traveling. And thus, even if you are at a constant speed, for example, if you're in a circular motion, you will still be accelerating, and this is the acceleration that I'll be referring to in this presentation. So what are the five variables in this equations? The first one is u, which is pertaining to initial velocity, v, final velocity, a, acceleration, t for time taken, and s for distance traveled. An acronym to remember this is SUVAT, and you can see here you have the SUVAT and their pertinent forms or their representations. So S is distance, for example. Alright, so the four magical equations. The first one is V equals to U plus AT. Second one, S equals to 0.5 times U plus V times T. Third one, V squared equals to U squared plus 2AS. And the last one, S equals to UT plus 0.5 AT squared. The first equation, V equals to U plus AT. This is technically the definition of acceleration, because acceleration is the change in final velocity and initial velocity over the time traveled. All you need is a little basic algebra and a little basic rearranging, and here you have this equation. This is a pretty amazing equation if you think about it, because all you need to have is the initial velocity, the acceleration, and the time of travel, and you have the final velocity. This is very applicable in many cases, such as like the picture you see right here of a race car. You can find out the final velocity. The second equation is S equal, as you can see above. This is a definition of average velocity. We first have AV, or average velocity, is equal to the distance traveled, which is S, over T, which is time. A little algebra, like you can see here, will lead us to the equation S equals to 0.5 T, V plus U, which is the final velocity plus the initial velocity times time divided by 2. What this basically can tell us is the distance traveled as long as we have the initial velocity, final velocity, and the time. The third equation can be derived from the first two. As you can see, as I just showed you, S equal to 0.5t in the previous equation. All we need to do is substitute the first equation into the second one, and you can see how we can get S equals to ut plus 0.5 at squared. What this equation tells us is the distance traveled if we have the initial velocity, the time, and the acceleration of the object. An important note to remember that is the initial velocity is not necessarily always going to be a quantity greater than 0. It can be 0. For example, if an object is dropped from a height, it will have an initial velocity of 0 because there's no force applied on it when it was initially dropped. The last equation is a little complex, and it uses the third equation and the definition of acceleration. So as you can see, we can use the definition of acceleration to get the value of t. T is equal to v minus u over a. This t value can be plugged into the third equation, and everywhere there's a t, all you have to do is plug in this equation. As you can see, there's a little algebra right here, and it's continued on the next slide. This is some more algebra, and here we go. We get 2uv gets crossed out, and you're left with 2as equals to v squared minus u squared. However, switching that around gives you v squared equals to u squared plus 2as. What this will tell you is the final velocity is equal to the initial velocity squared plus 2 times the acceleration times the distance traveled. So this is a conclusion of the four equations that I've shown you. An important thing to note is that In some cases, some variables are missing, in other cases, others are. For example, in this particular equation, there's no time. And in this situation, since there is no time, what happens is that you can use the other three variables to find the missing variable. For example, if you're given the initial velocity, the acceleration, and the distance, the final velocity can be computed without any knowledge of the time. Practice problems. The first question. Calculate the velocity of a race car accelerating uniformly by 5 meters per second square on a racetrack for 8 seconds. So let's analyze what variables we're given. First of all, we're given the initial velocity, which is 0. Like stated before, initial velocity can be 0. And we're also given the time traveled and the acceleration. So how do we calculate the velocity? Let's see. The equation that can be used is v equals to u plus at. And as you can see, the answer we can get is 40 meters per second. Very simple problem. Question 2. Calculate the final velocity of a billiard ball after 4 seconds of being hit, and it moves a distance of 10 meters. All resistive forces can be ignored. What this means is that no energy is lost or dissipated. So the variables that we were given were the time and the distance, and we have to find the velocity. So in here we can use s equal to 0.5t u plus v. Once again, u is 0 since the billiard balls were not moving initially, and as you can see, the velocity we can compute is 5 meters per second. A very simple problem that we can find the final velocity from just a few pieces of information such as the distance traveled and the final velocity. The time traveled. The question 3. What is the time it takes for an object to drop from a height of 196.2 meters when the object is under free fall? The answer is shown here. As you can see, s equals to ut plus 0.5 at squared. This was the third equation. In this case, s is going to be a negative number because s is actually delta s, and delta s is the final state minus the initial state. In this case, the final state was a lower state or lower height than the initial state, and thus the number is negative. The initial velocity is once again 0, and thus it cancels out the first term on the right hand side. And as you can see, t squared is computed for, it gets 40, and it's a 6.32 seconds. So it will take this particular ball 6.32 seconds to drop from a height of 196.2. Obviously, air resistance is not considered. The final question is a little tricky. An object falls from a height above the ground with an initial speed of 2 meters per second and a final velocity of 35 meters per second. How high above the ground was the object dropped? Now, though initially this question may seem as having insufficient information, however, the variables given, and some are unimplied, can give you the final answer. The equation that can be used is the fourth equation. Alright, so on the left hand side we have velocity squared. On the right hand side we have u squared plus 2as. We were given v and u, however we were asked to find s. In this case, acceleration is not given. However, it is an unimplied variable as the object is under free fall, and under free fall the only force acting upon it is gravity, and the acceleration of gravity is negative 9.81, as you can see here. From negative 9.81 and the two variables given in the question, s can be easily computed for. Once again, s is going to be a negative number because 0 minus a positive number will give a negative number since you're calculating final state minus initial state, and thus the object was dropped at a height of 124 meters. As a final note to this presentation, just keep in mind that these equations are for describing the motion of a object where it is undergoing uniform acceleration. So if you're given a few variables, you can find the other variable. For example, if you're given final velocity, you can use one of the equations to get time, for example. And thank you for watching, and I hope you learned about the uniform acceleration motion due to this presentation. Thank you.